Math 1314, Tyler Junior College, section 4.1, exponential functions. Exponent rules review. What I'm about to show you won't be specific questions in a homework assignment per se, but as we move forward, there are certain exponent rules we're expected to use, not just in this section, but in future sections in this chapter. On the board, you'll notice I've got a lot of descriptions on when to do things. In most classes, when they review exponent rules, they just throw them up there and say, here they are. But most exponent rules are more like instructions. When do I do this? When do I do that? When do I not do this? And so I've decided to categorize these rules mostly by what they tell you to do, with the exception of these three over here. For example, when to add exponents. The time to add exponents is when you're multiplying two expressions with the same base. So we'll say b and b. That might have different exponents, so we'll call the exponents x and y. If you are multiplying two exponential forms with the same base, then you keep the base and then you add the exponents. For example, if we had 2 to the third power times 2 to the fourth power, this rule says that you keep the base, and then you add 3 plus 4 to get 7. The reason is real simple. And I'm sorry, I'm assuming everybody knows how exponents work. But if you had something like 2 to the third power, it means 2 times 2 times 2. And if you have 2 to the fourth power, it means the same thing except 4 2's. The multiplication in between glues together these two multiplication problems into one long multiplication problem. And since an exponent counts how many times you multiply a base, you're just counting 3 and 4 for a total of 7 2's. So it's really a pretty easy rule to do. This is one that people typically remember. But the time to add exponents is when you're multiplying two exponential expressions with the same bases. When do we subtract exponents? Well, we add when we're multiplying expressions with the same bases. We subtract when we're dividing expressions with the same bases. But since division is typically written as a fraction, we'll put b to the x on top of b to the y. And this is the setup for when you subtract exponents. You keep the base the same, and then you subtract the exponents. So b to the x power divided by b to the y power equals b to the x minus y power. For example, if you wanted to evaluate 5 to the 13th power divided by 5 to the 11th power, you could work out both sides separately and then do the division problem, but this exponent rule simply says all you have to do is subtract the top minus the bottom. 13 minus 11 is 2, and then if we wanted to evaluate it, now it's easy, it's just 25. So the time the time to subtract exponents is when you are dividing two exponential expressions with the same base. So when do we multiply exponents? The time to multiply exponents is when you have a base, which we're calling b, and you raise it to some power, which we'll call x, but then you take that expression and raise it to another power, which we'll call y. So if we raise b to the x power to the y power, this is when we would multiply the exponents. The nice thing about this rule is that it looks correct. When you have back-to-back exponents, they almost look like a multiplication problem in their own right, and they are. So for example, if we had something like x to the third power raised to the fourth power, then we would just multiply 3 times 4 and get 12. Now this looks similar to the one up here, but be careful. The first one was multiplying two expressions with the same base. This third one is a single expression with a base raised to consecutive powers. So that's when you multiply. These three are fairly common. A lot of people remember those. But one that people tend to forget is when to divide exponents. Now we've actually seen this already. We saw it way back in section 1.6 when we were looking at other types of equations. One of those types of equations was rational exponents. So we've kind of seen this rule already, but it goes something like this. If you have a base raised to some power, which we'll call it x, but then you take some root of it, square root, cube root, or to be generic, let's say the wife root. Most books will put an n to say the nth root. I'm just using y for the index of the radical to be consistent with my choice of variables for the exponents. But if you raise a base to a power and then take a root, then you divide. The base stays the same, and the exponent is the power divided by the index of the radical. So for example, if you were taking the cube root of 7 to the 15th power, then you would just have to divide. Leave the 7, 15 divided by 3, and that would give 7 to the 5th power. I don't know 7 to the 5th power off the top of my head, or do I? Can I do it? 14,807? 14,800, I don't know if that's right or not. I just want to know. I know that's 7 to the 4th power, so I just got to do it with another 7. Anyway, that's not the point. The point is, if you take a root of a power, then you can divide the power by the index. That's going to be really helpful, especially for those of you heading towards calculus. Why? Calculus is easy if you can handle the algebra and the trigonometry, trigonometry being outside of this course. But as far as the algebra goes, when you do calculus, you do a lot of calculus to exponents. And things that aren't exponents, you try to write as exponents so that you can do calculus. So in calculus, when you see a radical sign, you are expected to turn it into just an exponent using this rule. And by the way, this actually applies to very small things like the square root of 49, which of course is 7. But we can rewrite this as an exponent because even something like the square root of 49 has an implied power and an implied index. When you don't see a power, you can assume it's 1. But if you add a radical and you don't see an index, you actually assume it's a 2. Square root meaning second root. And so the square root of 49 is the same as 49 to the 1/2 power. But again, we've had this discussion already way back in section 1.6. All right, rule number 5, when to distribute exponents. Just a reminder, you already know a distributive property that goes something like this. If you multiply one number, we'll call it A, times the sum of two numbers, we'll say B plus C. Then you can distribute the A to both halves of the addition problem and get AB plus AC. And it works if it's minus also. So you already know two distributive properties, one or two, it depends on your perspective. But when it comes to exponents, you have to be a little bit more careful because there are times when you can and times when you can't. There are two times when you can distribute exponents. Number one is when you have two bases multiplied together, so we'll say A times B, and that product is raised to some power, we'll say the x power. If you have a product raised to a power, then you can distribute the exponent to each factor in that product. So AB to the x power equals A to the x power times B to the x power. And you can distribute an exponent across a division problem, or commonly written as a fraction. So if we raise a fraction to a power, then you can distribute that power to both the numerator and the denominator. By contrast, there are two times when you cannot distribute, and I will warn you now, especially for those of you going into calculus. When you get to calculus and make the following mistakes, we get upset. Some of us get angry. Some of us want to throw things. Because by the time you get to calculus, you should stop making bad algebra moves. Here's a very common one. If you have an addition problem, we'll say A plus B, raised to some power, you cannot distribute the power. You cannot say this equals A to the x plus B to the x. It's easy to say don't do it. And in calculus, people still do it. And I'm not just talking calculus 1. I'm talking calculus 1, calculus 2, calculus 3. At some point, some of these people might actually become engineers, do this by mistake, and build a bridge that collapses. So don't do this. And you cannot distribute across subtraction. Instead of writing it twice, I'm just going to write plus minus, which is a lazy way of saying this is two rules. Don't distribute a power across addition, don't distribute a power across subtraction. It's tempting and it's also incredibly wrong. Now, that being said, if you go into theoretical math, there are some branches of math where this is a valid rule, but not in calculus, so don't do it. Have I made myself clear? All right, so you can distribute exponents across multiplication and division. You cannot distribute them across addition and subtraction. And I want to show you a gimmick for remembering when you can and cannot. You know the order of operations, please excuse my dear Aunt Sally. Most people write it like this, PEMDAS. I don't. I write it like a totem pole, and I put multiplication and division on the same level and addition and subtraction because neither one takes precedence over the other. If you see an arithmetic problem with both multiplication and division, you work them left to right. Same thing with addition and subtraction. A gimmick for remembering when you can and cannot distribute is you can only distribute across the thing below you. So for example, exponents can distribute across multiplication and division. Multiplication and division can distribute across addition and subtraction. You do have to be a little careful with division. You can only distribute it on one side, not the other, but let's not sweat that. You can only distribute from one level to the next. You cannot distribute by skipping a level. You cannot distribute an exponent across these two guys. So a visual gimmick for helping you remember when you can and cannot distribute. All right, let's talk about these last few rules. Zero exponent, I'll just give it to you. If you take any base, by the way, this rule is when the base is not equal to 1. If you take any base and raise it to the 0 power, you get 1. Don't believe me? Check with your calculator. Choose a number, 1 to the 0 power is 1. The base can't be 0. If you raise any base to the 0 power except 0, you'll get an answer of 1, and your calculator knows this. Choose any non-zero number, raise it to the 0 power, and you'll get 1. Now, if you want to push the boundaries and say, what about this? You'll have to wait until you get towards the end of Calculus 2, and you start talking about limits and something called L'Hopital's rule. 0 to the 0 power is technically undefined, but if you approach it, remember the arrow notation from talking about asymptotes? If you approach 0 to the 0 power, it can actually equal anything, depending on the situation. It's called indeterminate. But that aside, any non-zero number raised to the 0 power is equal to 1. For negative exponents, if you take any base and raise it to a negative power, we'll say negative x. A negative exponent says to reciprocate the answer to the positive exponent. In other words, to do a negative exponent problem, you do the positive exponent problem, but take the reciprocal by putting it under a 1. For example, if I asked you what 5 to the negative 2 power is, you would take 5 to the positive 2 power and put it under a 1. So you would get 1/25. So it's a pretty easy rule. It's not super intuitive, but the reason for it is not that hard to explain. If you look right here, and replace the x with zeros, the top becomes a 1. 0 minus y is negative y, and you get that rule. I know that says x's, this says y's, but the names of variables are actually immaterial. So it's just a direct consequence of when to subtract exponents. And as far as rational exponents, well, again, we've had this discussion before back in 1.6 when we talked about rational exponent equations. But a rational exponent is an exponent that's a fraction. But honestly, we've already talked this talk because it's just this property backwards. When you raise a number to a fraction power, the top does represent the power, the bottom represents the index to a radical. I do want to remind you, though, that in a situation like this, you can actually do the radical first and then save the power for last. We'll demonstrate some of these in the next video when we start graphing some of these basic exponential functions.